Welcome everyone. Today we're going to look at a simple C program, and in this C program we have some string in the trial1.txt, and we are simply writing that value into that string into trial_2.txt. What I mean is this. So we have, let's go to the desktop and cat trial1. We have hello Evelyn, and let's cat trial2. We have nothing, so we are simply going to write hello Evelyn into trial2. And this is important for us because in Linux file handling is pertinent because, well, it follows the philosophy of everything is a file, so we need to know how to handle files in Nasm. Okay, so on the right hand side we have the C code. We open the file, which is the first one, which is the trial one. We open the file, we read the file into a buffer. Then we open the second file, we write the buffer into the second file, then we close both files. Okay, and so let me save this and run this and show you guys how it works. Let me compile. And so let's see. This is the desktop. Let's start trial2 again, and then we see that it now contains hello Evelyn. Okay, so let me remove trial2, and let me touch trial2 again. So this time around we try to cast trial2. It should say nothing is in trial2. Okay, so we've basically cleaned it. So now let's look at the Nasm code for that. Okay, so the same setup. We have file1, file2, the path to file1, file2 here, and we also have the cases where when we try to open the file and there's an error, we have file could not be opened and the length of the error. So the same thing, file could not be opened and the length of the error. Always remember to add the 0 after the null terminator, which represents 0. And of course over here we have an uninitialized buffer, so we write it under the BSS section. We've already seen this, and now we're going to begin the code itself. So over here, firstly we open the file. Okay, so here we're going to open the file, or open file1. Okay, and we know our setup to be this: move RSI, then move RDX something, and then we do a syscall. So how then do we open the file1, and what exactly goes into the RAX register? It just so happens that this really nice website, the rchapman.org, is a blog, has listed lots of things, and to do a sysopen, we basically have to pass in a 2 into the RAX register. The RDI now contains the file name, the RSI contains flags, and the RDX contains the int mode or the permissions. Okay, so RAX now contains 2. RDI will contain the file name, as we've already seen, so it's essentially following the same thing. So open is 2, file1, we pass in file1, then we pass in the read only, and read only is basically its integer is basically 0, and we pass in our permission 0644, which essentially tells us that we already know how permissions work. So for example, if I do say MSL, these basically tell us the permissions. Okay, so over here we have 744. Okay, we have the read, write, execute, read, write, execute, like that. And the first 3 is for the owner, the next 3 is for the group, and then the third is for the others. And then 644 basically means that when we write 6 into binary, we have 110, and whenever the bit is set, it means we're going to write the RW and 4 is 100. So we only have R. The same thing over here. 4. We have R. This this is basically Linux basics. So it's nothing new over here. So after opening the file, we do a syscall. Then over here we see on the right hand side that we check whether the file is -1 or basically error. Now how do we go about this? We do a test REX. We know that the REX contains the value, or like the return value for the open syscall. Now we're going to use the operation called the test. And over here, mind you, the test basically does a bitwise end, so it's the same as writing the end REX, okay, against itself. But why do we use the test and not the end? And also, why is it that over here it's an if and not compare, where I'm not writing compare up to -1? It just so happens that over here in C, it's quite simple that we just do if it's -1, but it could just be any negative value, in the sense that perhaps it could return some error where the permissions for the file could not be opened, and it could just be any negative value besides 1. Okay, and that's why I'm not using the compare. Now, why aren't I using the end? It just so happens that, well, if we do, let's look at these two scenarios, yeah? So say we pass in a file descriptor to REX, then we do a test, and then we check a flag, okay? And then over here, we also check another flag. This time around, we see that over here, we're using the test, and here we're using end, okay? So when we pass in the file descriptor into REX, let's say, for example, the file descriptor is 5, okay? And we are passing it into REX, and we are doing 5 against 1, which is a bitwise end, because I'm saying the test is the same thing as the end. So we're doing 5 against end. 5 and 1. The bitwise end, 5 and 1, where 5 is 101 in base 2 and 001. We do a bitwise end, and we see that the solution is 001. Okay. And that's a result for like the second part. But this time around, because n is destructive, it means our result in itself is going to be placed into REX. So REX is now going to contain 001. Okay. And when we use REX for any further computation, it means REX is now 1, and that's not exactly what we needed. All we just needed to check was whether the least significant bit was 1, okay? And so the test in itself doesn't actually place 1 into REX, but rather it just checks the sign, okay? So basically it's just going to tell us that, oh hey, is the sign, is the bit actually 0 or not? And we're going to say jump if the bit is, or jump if it's 0. Okay, so JZ is basically a flag register. And these flag registers, they are unique, they are special registers. Perhaps sometime we'll talk about them some other time. But over here, we just seen that we just jump in if it's 0. And so REX still maintains its original file descriptor. And over here, REX, it forces, REX now becomes, it now becomes 1. Okay, so that's terrible. So perhaps we want to use the test instead of the end. And so essentially, over here we can use the end, but it's not preferred. The professionals will actually rather swallow us up. So let's just go with the test. And so we check, instead of the zeros, we are now checking the sign. Why are we checking the sign? And we're checking the sign whether it's negative, and if it's negative, we do a directive called exit failure. So we can write that directive here and say exit failure. Then we can, over here we do a write, and also we do a return value. Okay, but perhaps let's look at that later on. And so over here, so my point is, let me try to repeat what I'm saying. So my point is, REX could contain any negative value. Okay, so that's why we are not using compare REX to -1, because of the return value could be any of the NO codes, and it could be just negative something. And so we're using the test. Why are we using the test instead of the N? Well, the N works over here, the same thing, but basically the test is a choice, and that's we're also using over here. We're checking the jump if the sign. We're checking the sign of the results for the test. What do I mean by the sign? So, for example, say our return value is -5. Okay. Let me scroll. So -5. Okay, our return value is -5, which, well, it's represented this way in the computer. How do I know this? Because, well, 5 is this. We know the binary of 5 is 101, and because it's 8 bits, so we append like 5 zeros in front, so we have 5 zeros, 101. And to be able to find -5, we do the 2's complement. The 2's complement tells us that if we have 5, we invert each and every single bit. So when it's 0, it becomes 1, and then when it's 1, it becomes 0, that way. So now we have this, and then we simply add 1. Basically, this addition is subjected to any of the additions with carry, addition or carry propagation. So for example, the ripple carry or the Brent Kang, or I don't know, whichever addition you want. But basically over here, because there's no carry, so essentially 0 now becomes 1. And so this is -5 with 2's complement. Okay. And so basically the test is doing -5 again and -5, and basically the result is the same thing. Okay. And then because it's negative, the bit over here is set to 1. Okay. If it were positive, it would just be 0. So that's the main point I'm trying to say. So the test basically places this flag and sets this flag and lets us know that now the sign is negative. So when it's so if the sign is negative, then it goes to exit failure. Okay. Now let's write the exit failure some at a time, and let's continue on with our code. So we've checked okay, we've skipped the error, we'll write it later, and then over here the next thing that we do is we basically we store the value into the FD. Okay, so perhaps maybe I should write the FD here. FD, we reserve 1. We're using a 64. Let me write it this way: 64-bit integer size. Okay, so we have move FD array x. So we are now placing the array x value into the FD. Now, why do I have the square brackets? I have the square brackets there because if I had only written the FD, it would write it to an address, like, as in, it would just write it to an address. But with the square brackets, it's writing the value array x into the value at this address. I don't know if it's quite clear. Yes, and so we have this form, and then the very next thing that we do is we do a read. Okay, we're going to read and then place it into our read 1, sorry. So we're going to do a read system call. So read the FD file, or the file 1. And before I delete that, the read is 0. We're placing 0 into the array x. Then RDI now contains our file descriptor. So we have 0 file descriptor buff and 20. So essentially it's the same thing that when Mr. Toggles says that when he looks at the C code, and then he can basically know how the Nasm works. This is how it works, because basically the read value is going to go into the array x. The next one goes into the RDI. The next one goes into the RSI. The buff, and the next one goes into the RDX, and then we do a Syscall. Okay. And so now that we have this, after the reading, we're going to place the buff read at the value at that point. We're going to place in the byte at that point. We're going to place in the null terminator. Okay, so we're going to have move the read 1. Basically, I have to write the read 1. Firstly, read 1. we're reserving another 64-bit integer for the read. Basically replacing the read with the results of the read into read1. Okay, so array x, then we do the byte at this point plus read1, and then we're going to place in 0, which is a null terminator. Now, why wouldn't this work? This wouldn't work because basically the buff is, say, an address. Okay, let's write something like this, and we're saying that read1 over here, read1 actually represents an address, so it's basically going to do something like this also. So the addition is going to be more than actually the size of 20 that we actually reserved. Okay, so another thing is, perhaps one might think we do something like this. Okay, which actually makes sense, but for some reason this didn't work for me when I tried it out. So perhaps what we're going to do now is we're going to place into R9 the value of read itself, read1 itself. Then we're going to pass in the R9 value here instead. Okay, so now R9 contains the file descriptor, the read results. So let's say it read, I don't know, 10. Then it's just going to do, let's say it read, R9 is containing, say, I don't know, 5. Then it's going to write the whole thing. Then it's going to do plus 5, which essentially is going to yield this. So at this point, at this address, we're going to place in 0. Okay, I'm not quite sure if it's clear. And basically, after doing that, then we can open our second file descriptor. Okay, so how do we open the second file descriptor? We follow the same thing. So open second file, which is the file 2. So essentially we have this. Let me paste it here. Then instead of file 1, we have file 2. Okay, and then we're going to test. We're going to do the testing, which is checking the errors. So we have test the REX, that means REX, and jump if it's the sign. We're going to jump exit failure, and of course we're going to place it into SFD REX. Let me write the SFD here. SFD and reserve, another one, and then yes, we have it into that. Okay, then finally we once again write the buff into the second file descriptor. So we write buff to our second file descriptor. So essentially we have move REX1, move RD by the file descriptor here, then move RSI, our buff, and then move RDX read1. Or essentially we can do R9 because read1 and R9 now contain the same value. Okay, let me just do read1. Then do a syscall. Why read1 and not 20? Otherwise it will append like garbage to it, and that's not what we want. So we want the exact string size that we have. Okay, and the exact string size in the first file is, we have hello earthling. That's what's in the first file, and it counts as 15 when we count them, and then essentially at the 15 value we're placing in 0 for the null terminator, as we've already seen. So yeah, and so once we have this, we need to close the two files. Okay, so how then do we close the two files? Let's make a new, let me do this right now. How do we close the two files? Once again, when I bring up the website, we see that to close a file, the 3 goes into REX, and then our file descriptor goes into RDI. Okay, so 3 goes into REX, and our file descriptor goes into RDI. Then we do a syscall. So we've closed the first file. We need to also close the second file. Then finally we can exit successfully. Okay, and to exit we've already seen it's 60. Once again, when I open the website again, we look at 60. 60 goes into the RAX, and then the error code goes into the RDI. Okay, so 60, make RDI successful, so 0, and then we do a syscall, and then now we can look at the failure. So in the case where it fails, we want to write to the standard error. Okay, so we write to the standard error, move RAX1, move RDI, standard error is 2, and then move RSI, file error, and move RDX, error length, and then we do a syscall. The file error and the error length are already defined up above here, here on these two lines. Okay, so let's save this, and then hopefully it works. Okay, so once more, let me open up the second file, which is file 2. Over here we see the file 2 is empty, so let me close this. Yeah, let me save this, and then let me try to run fourth. For some reason I named it fourth because I'm running out of names. Okay, so it says read one is not defined. Okay, so let me go back. Fourth, 39, 40, and 61. Oh, it's capital. I made a capital here, I made it small. Okay. Okay, so run fourth. Okay, it's fine. And then we run fourth. And then let's go open our second file. So our second file, file 2, contains nothing. Why is that so? Why doesn't it contain anything? Why doesn't it contain anything? Okay, so let me look back at the code. And trial 2, trial 1. Let's see the problem. So in opening the second file, we need to read and write. Okay, so our value over here is supposed to be 2, not 0, because read only, this is the flag for read and write. Okay, yeah, this one, and then read only is 0 for the first file. Okay, so read and write. So basically, let me save this once more, and then let me try to run the code again. And then let's look at fourth. First, let me open the file and see whether, okay, it's empty. And then let me run the fourth. Let me open the file again. Oh, and then it shows. So, hello world, Earthling. Okay. Yeah, I nearly went crazy about that. Okay, so basically that's what I wanted to show you guys, that whenever you write a C code, there is a one-to-one correlation with the Nasm code, and it's not so difficult to get into writing Nasm. So yeah, I hope you guys learned something today, and yes, if I said anything wrong, please correct me in the comment section, and I'll be happy to take a look at it. So thank you very much for watching, and see you next time.